So let's look at the first question here. Will the time interval between the instance at which they hit the ground be longer than, shorter than, or equal to 1 second? And so in this particular case, since I release the objects 1 second apart, but otherwise their motions are identical, I release them from rest, they're accelerating in a gravitational field, they're falling. They're both falling for the same amount of time because their motions are identical, so they'll hit the ground exactly 1 second apart. So the next question asks, will the difference in their speeds increase, decrease, or stay the same? So in order to understand this, we're going to draw velocity versus time graphs for the two stones. In order to make this simple, we're going to actually choose, in this case, the positive direction of the motion to be downward, because otherwise we'll have too many minus signs running around and it will be confusing. So let's draw a velocity versus time graph. So here's my vertical axis, which is going to be velocity. And the horizontal axis is going to be time. And we can draw on here the motions of both of the stones as they fall. And so if we look at the motion of the first stone as it's falling, let's call the time that it starts time t equals 0. And so we know that that stone is going to fall with ever increasing velocity because it's a constant gravitational acceleration. And so the first stone is going to have a velocity that kind of looks like that. And then once I release the second stone, sometime later, its motion is going to be identical, but it's just going to be delayed by a second. So I'm going to have a second line that looks like this, and this is going to be v2. And so these are the velocities of both of the objects as a function of time. And so the question asks, will the difference in their speeds increase, decrease, or stay the same? Since these are two parallel lines with the same slope, then once stone 2 starts moving, the difference in their speeds, which I'll write as delta v, but it's not a vector difference, but I'm just going to write it as delta v. Delta v is really v1 minus v2 in this case. This difference stays constant with time because both of these objects are accelerating at the same rate. So both of these lines have the same slope, so the lines are actually parallel. So the difference in their speeds stays the same as you go. Now, we can actually write this out mathematically instead of drawing a picture. So let's do that next. So we know that stone 1 is going to have an equation of describing its velocity that's going to look like v1 is equal to g times t1, where t1 is the time that stone 1 has been traveling. We also know that we drop stone 2 1 second after t1 starts moving. So t2 is really t1 minus 1. And of course, this is only valid for t1 greater than 1 second because time t2 isn't negative. So once t2 starts moving, its time is t1 minus 1. OK, so now that we know that that's true, we can write that v2 is equal to g times t2. And I can substitute then t2 in, I can substitute this equation in for t2. So I know that v2 is equal to g times t1 minus 1. So if I multiply that out, I get that v2 is equal to gt1 minus g times 1 second. And so if I want to write the difference in the two speeds here, I can write that v1 minus v2 is going to be equal to gt1 minus this quantity here. So that's gt1 minus gt1 minus g times 1 second. And so the difference in these two speeds, v1 minus v2, is equal to g times 1 second, meters per second. And so you can see that this is constant. And that is exactly the separation between these two lines as the two stones are falling. So the difference in their speeds, as we already shown in the picture, is constant. And now we've actually written down the value. It's g. OK, so the last part of this question asks, for the two stones, will the separation increase, decrease, or stay the same? So separation is position, and so we're going to draw a position versus time graph for constant acceleration and look at the relative motions of the two stones. So again, we're going to define the positive direction to be down so that we can actually have positively increasing values, and so it's just easier to draw that way. So I'm going to draw a velocity versus time graph here. Sorry, position versus time graph here. So this is my vertical position. The horizontal axis is going to be time. And so what I'm going to want to do here is to draw the motions of the two objects as they fall. And so we know that the displacement, the position, is going to increase quadratically because I have constant acceleration. So the first projectile is going to look something like this. It's going to be a parabola. So this is y1 as a function of time. And then the second one is going to look like this. I'm going to release it at a time t equals 1 second, and it's going to have a parabolic shape as well. And so as I look at the difference in these two positions as they go up, you can see that when stone 2 starts moving, stone 1 has already traveled some distance. Stone 1 is always moving faster than stone 2 because it has a larger speed. And so this difference in their positions increases with time. You can see it's growing very large as I try to draw the separation between these two as it moves along. So the separation increases dramatically with time. Now there's another way of saying that in some sense. So we could say that we know that V1 is greater than V2 always, because we found in the last time that the difference between their two speeds was equal to g times 1 second. So if V1 is always greater than V2, then over any time interval, the distance that V1 travels, which is equal to V1 times some time interval, has to be greater than the distance that stone 2 travels, which is V2 times the same time interval. So no matter what we do when these stones are falling, because V1 is always greater than V2, over any time interval, the distance that stone 1 has traveled is larger than the distance that stone 2 travels during the exact same interval. So that's always true, and so the separation between these two things only increases as they fall. Now I leave it as an exercise for you to actually calculate what that separating distance is as a function of time by using t2 is equal to t1 minus 1, and using our kinematic equation, y final is equal to y initial plus v initial t. In this case, it's going to be plus 1/2 gt squared because we define the positive direction to be down. And using that to calculate the positions of the two stones and the difference between them as a function of time.